Calcium metabolism refers to all the movements, and how they are regulated, of calcium atoms and ions into and out of various body compartments, such as the gut, the blood plasma, the interstitial fluids which bathe the cells in the body, the intracellular fluids, and bone. An important aspect, or component, of calcium metabolism is plasma calcium homeostasis, which describes the mechanisms whereby the concentration of calcium ions in the blood plasma is kept within very narrow limits. Derangements of this mechanism led to hypercalcemia or hypocalcemia, both of which can have important consequences for health. In humans, when the blood plasma ionized calcium level rises above its set point, the thyroid gland releases calcitonin, causing the plasma ionized calcium level to return to normal. When it falls below that set point, the parathyroid glands release parathyroid hormone, PTH, causing the plasma calcium level to rise. Calcium concentrations. Calcium is the most abundant mineral in the human body. The average adult body contains in total approximately 1 kilogram, 99% in the skeleton in the form of calcium phosphate salts. The extracellular fluid, ECF, contains approximately 22 mmol, of which about 9 mmol is in the plasma. Approximately 10 mmol of calcium is exchanged between bone and the ECF over a period of 24 hours. The concentration of calcium ions inside the cells, in the intracellular fluid, is more than 7,000 times lower than in the blood plasma, i.e., at less than 0.0002 mmol per liter, compared with 1.4 mmol per liter in the plasma. Function. Calcium has several main functions in the body. It readily binds to proteins, particularly those with amino acids whose side chains terminate in carboxyl COOH groups, e.g., glutamate residues. When such binding occurs, the electrical charges on the protein chain change, causing the protein's tertiary structure, i.e., three-dimensional form, to change. Good examples of this are several of the clotting factors in the blood plasma, which are functionless in the absence of calcium ions, but become fully functional on the addition of the correct concentration of calcium salts. The voltage-gated sodium ion channels in the cell membranes of nerves and muscle are particularly sensitive to the calcium ion concentration in the plasma. Relatively small decreases in the plasma ionized calcium levels, hypocalcemia, cause these channels to leak sodium into the nerve cells or axons, making them hyperexcitable. Positive bathmotropic effect, thus causing spontaneous muscle spasms, tetany, and paresthesia, the sensation of pins and needles of the extremities and round the mouth. When the plasma ionized calcium rises above normal, hypercalcemia, more calcium is bound to these sodium channels, having a negative bathmotropic effect on them, causing lethargy, muscle weakness, anorexia, constipation and labile emotions. Calcium acts structurally as supporting material in bones as calcium hydroxyapatite, circa 10, PO4, 6. O2. Because the intracellular calcium ion concentration is extremely low. See above. The entry of minute quantities of calcium ions from the endoplasmic reticulum or from the extracellular fluids cause rapid, very marked, and readily reversible changes in the relative concentration of these ions in the cytosol. This can therefore serve as a very effective intracellular signal, or second messenger, in a variety of circumstances, including muscle contraction, the release of hormones, e.g., insulin from the beta cells in the pancreatic islets, or neurotransmitters, e.g., acetylcholine from presynaptic terminals of nerves, and other functions. In skeletal and heart muscle, calcium ions released from the sarcoplasmic reticulum. The endoplasmic reticulum of striated muscles binds to the troponin C present on the actin-containing thin filaments of the myofibrils. The troponin's 3D structure changes as a result, causing the tropomyosin to which it is attached to be rolled away from the myosin-binding sites on the actin molecules that form the backbone of the thin filaments. Myosin can then bind to the exposed myosin-binding sites on the thin filament to undergo a repeating series of conformational changes called the cross-bridge cycle, for which ATP provides the energy. During the cycle, each myosin protein paddles along the thin actin filament, repeatedly binding to myosin-binding sites along the actin filament, ratcheting and letting go. In effect, the thick filament moves or slides along the thin filament, resulting in muscle contraction. This process is known as the sliding filament model of muscle contraction. Normal ranges. The plasma total calcium concentration is in the range of 2.2 to 2.6 mmol per liter, 9 to 10.5 milligrams per deciliter, and the normal ionized calcium is 1.3 to 1.5 mmol per liter, 4.5 to 5.6 milligrams per deciliter. The amount of total calcium in the blood varies with the level of plasma albumin, the most abundant protein in plasma, and therefore the main carrier of protein-bound calcium in the blood. The biologic effect of calcium is, however, determined by the amount of ionized calcium, rather than the total calcium. It is therefore the plasma ionized calcium level which is tightly regulated to remain within very narrow limits by a set of negative feedback systems, or homeostats, which constantly measure and correct any deviations from normal. Calculating the ionized calcium concentration from the total calcium concentration in the plasma, with different plasma albumin levels. Between 35 to 50% of the calcium in plasma is protein-bound, and 5 to 10% is in the form of complexes with organic acids and phosphates. The remainder, 50 to 60%, is ionized. The ionized calcium can be determined directly by colorimetry, or it can be read off from nomograms, though the usefulness of the latter is limited when the pH and protein content of the plasma deviate widely from the normal. Effector organs. Absorption from the intestine. The normal adult diet contains about 25 mmol of calcium per day. Only about 5 mmol of this is absorbed into the body per day. See below. Calcium is absorbed across the intestinal epithelial cell's brush border membrane and is immediately bound to calbindin, a vitamin D-dependent calcium-binding protein. Calbindin transfers the calcium directly into the epithelial cell's endoplasmic reticulum, through which the calcium is transferred to the basal membrane on the opposite side of the cell, without entering its cytosol. From there TRPV6 and calcium pumps, PMCA1, actively transport calcium into the body. Active transport of calcium occurs primarily in the duodenum portion of the intestine when calcium intake is low, and through passive paracellular transport in the jejunum and ileum parts when calcium intake is high, independently of vitamin D level. The active absorption of calcium from the gut is regulated by the calcitriol, or 125-dihydroxycholecalciferol, or 125-dihydroxy-vitamin D3 concentration in the blood. Calcitriol is a cholesterol derivative. Under the influence of ultraviolet light on the skin, cholesterol is converted to provitamin D3, which spontaneously isomerizes to vitamin D3, or cholecalciferol. Under the influence of parathyroid hormone, the kidneys convert cholecalciferol into the active hormone 125-dihydroxycholecalciferol, which acts on the epithelial cells, enterocytes, lining the small intestine to increase the rate of absorption of calcium from the intestinal contents. Low parathyroid hormone levels in the blood, which occur under physiological conditions when the plasma ionized calcium levels are high, inhibit the conversion of cholecalciferol into calcitriol, which in turn inhibits calcium absorption from the gut. The opposite happens when the plasma ionized calcium levels are low. Parathyroid hormone is secreted into the blood and the kidneys convert more cholecalciferol into the active calcitriol, increasing calcium absorption from the gut. Since about 15 mmol of calcium is excreted into the intestine via the bile per day, the total amount of calcium that reaches the duodenum and jejunum each day is about 40 mmol. 25 mmol from the diet plus 15 mmol from the bile, of which, on average, 20 mmol is absorbed back into the blood. The net result is that about 5 mmol more calcium is absorbed from the gut than is excreted into it via the bile. If there is no active bone building, as in childhood, or increased need for calcium during pregnancy and lactation, the 5 mmol calcium that is absorbed from the gut makes up for urinary losses that are only partially regulated. Most excretion of excess calcium is via the bile and feces, because the plasma calcitriol levels, which ultimately depend on the plasma calcium levels, regulate how much of the biliary calcium is reabsorbed from the intestinal contents. Urinary excretion of calcium is relatively modest, about 5 mmol per day, in comparison to what can be excreted via the feces, 15 mmol per day. Not all the calcium in the diet can be readily absorbed from the gut. The calcium that is most readily absorbed is found in dairy products and eggs, as well as in tinned fish products. The calcium contained in vegetable matter is often complexed with phytates, oxalates, citrate and other organic acids, such as the long-chain fatty acids, e.g., palmitic acid, with which calcium binds to form insoluble calcium soaps. The kidneys. The kidney filters 250 mmol of calcium ions a day in pro-urine, or glomerular filtrate, and resorbs 245 mmol, leading to a net average loss in the urine of about 5 mmol. The quantity of calcium ions excreted in the urine per day is partially under the influence of the plasma parathyroid hormone, PTH, level. High levels of PTH decreasing the rate of calcium ion excretion, and low levels increasing it. However, parathyroid hormone has a greater effect on the quantity of phosphate ions, HPO42-, excreted in the urine. Phosphates form insoluble salts in combination with calcium ions. High concentrations of HPO42- in the plasma, therefore, lower the ionized calcium level in the extracellular fluids. Thus, the excretion of more phosphate than calcium ions in the urine raises the plasma ionized calcium level, even though the total calcium concentration might be lowered. The kidney influences the plasma ionized calcium concentration in yet another manner. It processes vitamin D3 into calcitriol, the active form that is most effective in promoting the intestinal absorption of calcium. This conversion of vitamin D3 into calcitriol is also promoted by high plasma parathyroid hormone levels. See below. The role of bone. Although calcium flow to and from the bone is neutral, about 5 to 10 mmol is turned over a day. Bone serves as an important storage point for calcium, as it contains 99% of the total body calcium. Calcium release from bone is regulated by parathyroid hormone, PTH, in conjunction with calcitriol manufactured in the kidney under the influence of PTH. Calcitonin, a hormone secreted by the thyroid gland when plasma ionized calcium levels are higher, rising. Not to be confused with calcitriol, which is manufactured in the kidney. Stimulates incorporation of calcium into bone. A low calcium intake may be a risk factor in the development of osteoporosis in later life. In one meta-analysis, the authors found that in 50 out of the 52 studies that they reviewed, a diet adequately rich in calcium reduced calcium loss from bone with advancing postmenopausal age. A diet with sustained adequate amounts of calcium reduced the risk of osteoporosis. Regulation of calcium metabolism. The plasma ionized calcium concentration is regulated to within very narrow limits, 1.3 to 1.5 mmol per liter. Despite being the central hub through which calcium is moved from one body compartment to the other. See diagram on the right. This is achieved by both the parafollicular cells of the thyroid gland and the parathyroid glands constantly sensing, i.e., measuring, the concentration of calcium ions in the blood flowing through them. When the concentration rises, the parafollicular cells of the thyroid gland increase their secretion of calcitonin, a proteinaceous hormone, into the blood. At the same time, the parathyroid glands reduce their rate of parathyroid hormone, or PTH, also a proteinaceous hormone, secretion into the blood. The resulting high levels of calcitonin in the blood stimulate the skeleton to remove calcium from the blood plasma and deposit it as bone. The reduced levels of PTH inhibit removal of calcium from the skeleton. The low levels of PTH have several other effects. They increase the loss of calcium in the urine, but more importantly inhibit the loss of phosphate ions via that route. Phosphate ions will therefore be retained in the plasma where they form insoluble salts with calcium ions, thereby removing them from the ionized calcium pool in the blood. The low levels of PTH also inhibit the formation of calcitriol, 125-dihydroxyvitamin D3, from cholecalciferol, vitamin D3, by the kidneys. The reduction in the blood calcitriol concentration acts comparatively slowly on the epithelial cells, enterocytes, of the duodenum, inhibiting their ability to absorb calcium from the intestinal contents. The low calcitriol levels also act on bone, causing the osteoclasts to release fewer calcium ions into the blood plasma. When the plasma ionized calcium level is lower, falls, the opposite happens. Calcitonin secretion is inhibited and PTH secretion is stimulated, resulting in calcium being removed from bone to rapidly correct the plasma calcium level. The high plasma PTH levels inhibit calcium loss via the urine while stimulating the excretion of phosphate ions via that route. They also stimulate the kidneys to manufacture calcitriol, a steroid hormone, which enhances the ability of the cells lining the gut to absorb calcium from the intestinal contents into the blood. By stimulating the production of calbindin in these cells, the PTH-stimulated production of calcitriol also causes calcium to be released from bone into the blood by the release of RANKL, a cytokine, or local hormone, from the osteoblasts, which increases the bone resorptive activity by the osteoclasts. These are, however, a relatively slow processes. Thus fast short-term regulation of the plasma ionized calcium level primarily involves rapid movements of calcium into or out of the skeleton. Longer-term regulation is achieved by regulating the amount of calcium absorbed from the gut or lost via the feces. Pathology: hypocalcemia, low blood calcium, and hypercalcemia, high blood calcium, are both serious medical disorders. Osteoporosis, osteomalacia and rickets are bone disorders linked to calcium metabolism disorders and effects of vitamin D. Renal osteodystrophy is a consequence of chronic renal failure related to the calcium metabolism. Research into cancer prevention. The role that calcium might have in reducing the rates of colorectal cancer has been the subject of many studies. However, given its modest efficacy, there is no current medical recommendation to use calcium for cancer reduction. Several epidemiological studies suggest that people with high calcium intake have a reduced risk of colorectal cancer. These observations have been confirmed by experimental studies in volunteers and in rodents. One large-scale clinical trial shows that 1.2 grams calcium each day reduces modestly intestinal polyps recurrence in volunteers. Data from the 4 published trials are available. Some 40 carcinogenesis studies in rats or mice, reported in the ChemoPrev database, also support that calcium could prevent intestinal cancer. See also: disorders of calcium metabolism, calcium in biology. Footnotes: calcium at lab tests online. Physiology: 5/5 of a chain, 6/5 of a chain, a 6-line, Essentials of Human Physiology.